let's build a waveguide. Building a waveguide 1.
IKEA step 1. So I guess we've already gone through some special properties of the rectangular waveguide, there being some standing wave in a cross section and then a traveling component coming out of the tube. But there are other shapes of waveguides as well, right? We could have circular and we could have some irregularly shaped waveguides. Let me ask you, is there also standing waves in these kind of waveguides?
Well, we are still going to get, if they're metallic, we're going to still get waves bouncing and getting trapped back and forth. It's just their shape and calculation is going to be a little harder, especially in this case. But they have something in common. In other words, there's a pattern in the perpendicular in the plane here, which is different. Square, circle, kidney bean shaped. And then the energy is going there. So we should divide everything up into a Z component and a transverse component. So you see that here, the electric field transverse means in the plane. Looking into
they can
the
be
waveguide.
in the Euclidean coordinate.
It could be whatever.
Familiar with.
So this one will give us, this is polar, this is some
or whatever it is,
numerical shape. Now, when we have standing waves here, we know it's sines and cosines, like in the tube that we used before. Here, it's a messy business called Bessel functions. So way more complicated to calculate when we're dealing with fiber optics. So here we have E perpendicular and the Z component. The same for H. And we've done that before, but this looks a bit new. We're dividing the gradient operator into two pieces, one that's in the plane of the waveguide and one along the Z-axis. And then we could substitute in. Take me through this, Sam.
Okay, so in this case, I guess we're just calling back to Maxwell's equation, where you take the curl of the E field. So in the grad operator, we just substitute in this broken up form and put it here. Same for the E field. We take the E field and plug in this separated form with the perpendicular and the traveling component and put it in here. And we get this, which we're also familiar with from the entire chapter 2 practices.
Right, and this is Faraday's equation in phasor form. And I guess, what can you say about Ampere's equation here? What's going to go in the blank?
Yeah, we can do the same business, right?
Let's do the blank. Yeah, let's see.
So for the gradient, we just substitute the same way like we did for above. So there's the perpendicular and the moving component in Z. And then we substitute in the broken up form of the H equation for H. So we get, don't forget the bracket. This.
Wonderful. So now what we get to do in step 2 is isolate the Z component of this equation and the perpendicular component. So that's what we're going to do in building a waveguide 2. We're going to look at the perpendicular components, and that's an exercise in cross product. Onwards to building waveguide 2.